Hi, this is week 9 of AP Physics, and in this week we'll be dealing with friction. So here we have it. Our lesson objective: students will be able to incorporate friction formulas with Newton's third law. Forces of friction: an object moving on a surface or through a medium, such as air or water, encounters resistance. That's referred to as friction. The force that counteracts a stationary object is called the force of static friction. So static is not moving. On the other hand, the force of friction of an object in motion is called force of kinetic friction. Kinetic meaning movement. Static friction is calculated using this formula. Fs for force of static friction is less than or equal to the coefficient of static friction multiplied times force normal. The value of coefficient of static friction depends on the surface that it's making contact with. For example, if an object is on ice, that constant is going to be very small. Because there's not a lot of friction. If an object were to be placed on sandpaper, and then the constant would be much greater because there is a lot more friction. A couple of things I wanted to mention. If the object for static friction, you put force on it and it's not moving, then the force of static friction will be the same as the force push. But if the object, someone puts force on it and begins to move, the force push, if they're pushing on it, will be greater than the force of kinetic friction. If I were to compare kinetic friction versus static friction for the coefficient, the value of the coefficient for static is greater than that of kinetic friction. In the graph here, you would have to put in energy until you reach a maximum, and at that point then the object will begin to move, and so it's no longer static anymore, and it goes to kinetic, and you notice the drop in the line. So static has a greater value than does kinetic. What is that value? Well, for kinetic it's calculated as such. Force kinetic is equal to the coefficient of kinetic friction multiplied times the force normal. So those are our formulas. Okay, an additional formula I also wanted to bring up is the constant for kinetic friction can also be found by dividing acceleration over gravity. Alright, now here are some values for static friction and kinetic friction, and as I mentioned earlier, static is greater than kinetic. Alright, so there you have from steel on steel, aluminum on steel, all the way down to Teflon on Teflon. In example 7, they ask you as the following question. Suppose a block with a mass of 2.5 kilograms is resting on a ramp. If the coefficient of static friction between the block and the ramp is 0.350, what maximum angle can the ramp make with the horizontal before the block starts to slip down the ramp? Okay, so they give us a coefficient and want to know how much can we tilt this ramp so it can go. So we're going to start with a free body diagram here. In this free body diagram, there's our object, and just represented by a dot. And the first vector arrow I'm going to draw is that of gravity, which goes straight down. Alright, so always straight down. Alright, that is force of gravity, which is most of the time though you'll see it written as mg. So I'm going to go ahead and start doing that. mg, because it's mass times gravity will give you force of gravity, which is weight. Next, I'm going to go with this arrow, I'm going to break it down into its components, to an x and y components. Alright, the y component is going to be a straight down the line that is going to be perpendicular to the ramp. Okay, so there we go. And the next line for our vector, for our component, for the gravity vector, is going to be down here on the x-axis. Alright, so we're going to call this one force of gravity on the x-axis, and this one force of gravity on the y-axis. Alright, next, on top, we have this force of gravity on the x-axis. Pardon me, that should say y-axis. That should be the same as the force normal, same in magnitude. Alright, so keep that in mind. These two, force of gravity on the y-axis and force normal, are the same in magnitude. So the same length, though force normal points up, force gravity points down. Alright, force gravity on the x-axis is going to be the same in magnitude as force friction. Force of friction, we'll put S for static friction. Okay, so now I want to get these values and actually hammer them out a little bit more. What exactly is force of gravity on the x-axis? Alright, so Let's go ahead and do that. The angle that we're looking for, theta, it'll be the same one here and inside the top of the triangle, and we're going to look at this one first. Notice how force of gravity in the x-axis is opposite the angle. So opposite, and we have the hypotenuse, which is gravity, opposite over hypotenuse, that's going to go ahead and be sine. So you need sine for that. So I'm going to write this down. Sine of theta, it's equal to opposite, force of gravity on the x-axis, over the hypotenuse, which I'm going to put mg for it, because like I said, force of gravity, most of the time you see it written as mg. If I multiply both sides by mg, that's going to help me isolate the force of gravity on the x-axis. So that cancels out. There we have it. Force of gravity on the y-axis is going to be very similar, though notice that it's adjacent to the angle, so therefore it is cosine, and we have the hypotenuse. So it's going to be mg times cosine of theta equals force of gravity on the y-axis. Alright, so those values are important to note. Now, I also want to point out that these two, particularly this section, is going to be the same in magnitude as force normal for the force of gravity on the y-axis, and force of static friction is going to be the same as force of gravity on the x-axis. They have the same magnitude. Alright, so our formula, force of static friction is equal. We're not going to say the less than because we're trying to get right up to the very edge before it begins to slip. It's equal to the coefficient of static friction multiplied times force normal. Now I'm going to begin to substitute. What is static friction? Well, I mentioned it was the same in magnitude as force of gravity on the x-axis. So I'm going to put mg times sine theta. Okay. And what's force normal? Force normal is the same magnitude as force of gravity on the y-axis. So I'm going to put mg times cosine theta. Alright. Next, I want to go ahead and I want to combine some like terms, and particularly the angles. That's really what I'm trying to combine. So I'm going to go ahead and divide by that. Mg times cosine of theta on both sides. And that's all gone. M and G are gone, and leaving us sine of theta over cosine of theta. Alright, so what is sine divided by cosine? The answer for that? Tangent. Sine divided by cosine is tangent. Okay, and I can show a little bit of work on that a little bit later on so you can get it. So for the angle, we want to isolate the theta, so we're going to get rid of the tangent. So we're going to do inverse tangent. Inverse tangent of the coefficient of static friction, that's going to give us the angle. So it's going to be inverse tangent of 0.350. So our answer for this problem would be, let's check it out. Inverse tangent, 0.35, 19.3 degrees. Okay, so that would be our answer for this problem. Alright, I do want to take a moment to discuss sine over cosine. Alright, so is sine over cosine really tangent? Alright, let's do some SOHCAHTOA. SOHCAHTOA, sine is opposite over hypotenuse. Cosine is adjacent or hypotenuse, and tangent is opposite over adjacent. Alright, so that's SOHCAHTOA. You learned that from your math class. Alright, so I want to focus on this part. Sine divided by cosine. So what is sine? Sine is opposite over hypotenuse. And cosine, we're going to divide by adjacent over hypotenuse. Alright, so for in your math class, how do you do this type of division? Well, you flip over the second and fraction and change that to a multiplication. There you go. So what's going to happen to my h's? They cancel out. So what I get? I get opposite over adjacent. Opposite over adjacent, that is tangent. Alright, so that's why we got that tangent right there. So that's the explanation on it. Alright, let's go ahead and move on to the next part. And up next is problem number 19. And in this problem, they ask you as the following question. How would a larger static friction coefficient affect the maximum angle? Okay, so if we were to make it bigger, right here, what if we were to increase this value? What would that do to the angle? Well, that would also increase the angle. Let's try it out just to make sure. Inverse tangent of, let's pick a bigger value, bigger than 0.35. Let's go with 0.400. That should give us a bigger angle since it is a rougher surface. Therefore, it will have a larger angle that you can tilt the ramp. So inverse tangent of 0.400 will give us an angle of 21.8. So can we make that proper statement? Yeah, if you increase the coefficient of static friction, you can get a bigger angle. The answer is yes. And here's, yeah, we went through the math. It works out. All right, let's go ahead and move on to our next problem, problem number 20. In this problem, they ask you the following question. It says the ramp in the previous example is roughed up and the experiment repeated. All right, so part A, what is the new coefficient of static friction if the maximum angle turns out to be 30? Okay, so let's go ahead and work this one out. So they're saying the new angle is 30. They roughed up the ramp. All right, and to figure out for the angle, we have this. Theta is equal to inverse tangent of the coefficient of static friction. So how do we, what if the new angle is 30? What will we do? Well, we would just use tangent of theta to get the new coefficient of static friction. So if they said that's 30 degrees now, so what we have to do is get tangent of 30, and that's going to give us a new coefficient of static friction. So I'll take care of part A. So tangent of 30 is 0.577. So that's your new coefficient of static friction. All right. So that takes care of part A for this problem. All right, in part B, they ask you guys find the maximum static friction force that acts on the block. All right, so static friction, what will be the maximum on it? All right, so I wanted to go ahead and go back to the original problem where they tell us that the mass of the block is 2.5 kilograms. So we're going to need that value. I'm going to write it over here. Mass of this block is 2.5 kilograms. All right, so again, they want to find the maximum static friction force that acts on the block. Okay, so static friction is, we're going to say it's equal to the coefficient of static friction times the normal force. And in this problem, normal force is the same as force of gravity on the y-axis. All right, and force of gravity, if you recall, we saw for it earlier, was really force of gravity, which is mg times cosine of theta, which is 30. All right, so because we have this value, now we have force normal. Okay, so in the place of force normal, I'm going to put that. So it's going to be the constant, and instead of force normal, it's really force of gravity on the y-axis, which is this, mass times gravity times cosine of theta. That's how we're going to go ahead and solve for it. They gave us the angle, which they said it's now 30 degrees, and we just solved for the coefficient. That's going to go right there. We know the mass that is there, and gravity, we're assuming we're on planet Earth, so it's going to be 9.88 meters per second, but to make our life easier, we usually use 10 meters per second squared. All right, so let's go ahead and plug in the values. So it is 0.577. Mass, it is 2.5 kilograms. Gravity is, running out of space here, 10 meters per second squared. And cosine of 30 degrees, barely squeezing that in there. All right, so let's plug it into the calculator. I'm going to start with cosine of 30, multiply times 10 times 2.5 times 0.577. So the maximal force of static friction has to be roughly 12.5 newtons. That would be the answer for part B of this problem. Alright, let's go ahead and move along. Our next problem is number 21. And in problem number 21, they ask you as the following. If you press a book flat against a vertical wall with your hand, in what direction is friction force exerted by the wall on the book? Alright, so let's pretend this is a book. I'm pressing it against the wall. Where is friction going? Is it A, upward, B, downward, out from the wall, or into the wall? Alright, in this scenario, alright, it's slowing me down, so it is upwards. Remember, friction slows you down. This calculator is not accelerating down, alright, so therefore it must be, something needs to be working against gravity, so it's going to be force of friction pointing up. So the answer would be A for this problem. If you're wondering, what about force normal? Force normal will be coming against, out of the board, which is what keeps me from putting it through the wall. Alright, so force of friction will be going up. Alright, let's go ahead and move on to our next problem, number 22. Problem number 22 says that a crate is sitting in the center of a flatbed truck. As the truck accelerates to the east, the crate moves with it, not sliding on the bed of the truck. Alright, so let's go ahead and do a quick diagram of that. So we have a flatbed truck. And it has a crate here. And it is accelerating. When I say east is that way. Next, the box doesn't slide as the truck accelerates. In what direction is the friction force exerted on the bed of the truck by the crate? Alright, is it to the east? Is it to the west? And there is no friction force, that's part C. It is not C. The answer is the friction would be to the east. Okay, and that would go ahead and keep it from moving. Why? Because the crate wants to slide towards the back, so the friction works against it. Alright, now in reality, is the truck moving that's going to create the illusion that the box sliding towards the back. In reality, it's staying still and it's the truck that it's moving. Alright, but the answer for this would be B, to the east. Alright. Let's take a look at our last problem, problem number 23. In this one, they ask you as the following scenario. Suppose your friend is sitting on a sled and asks you to move her across a flat horizontal field. You have a choice. You can A, push her from behind by applying a downward force, as you see in the picture, at 30 degrees below the horizontal, or option B here, you can attach a rope from to the sled and pull it at an upward force of 30 degrees above the horizontal. Which option is best and why? The answer to which is best is B. B is best. Now let's get into the why. The first force is being applied at 30 degrees, but you're pushing down. The next one, you're pulling at 30 degrees, but you're pulling up. Alright, now let's talk about force of gravity. Both force of gravity will be the same in both scenarios. So here's scenario A, there's gravity. Here's scenario B, here's gravity as well. I'm going to draw them the same length. Force, gravity, force of gravity. Alright, now let's break down this force push into its components. So right now it's diagonal, so I'm going to break it down into an X and a Y component. I'm mainly concerned with this one, force gravity on the force pull on the X-axis. That's what I'm concerned with. Notice how I have an additional arrow pointing down. So if I were to move it here, that's my force push on the X-axis. So I put it here. So now notice the whole length of this arrow. But that means we're going to need a force normal to match the length. Force normal, so to match the length of that. So we're going to ignore force push on the y-axis. It's not important. That's if they wanted us to figure out how fast they're accelerating, then we'll look at it, but we're not. Alright, now you look at the opposite where he's pulling up. So let's break this one down into the components. There'll be a force going this way and a force going up, since the arrow is that way. Now the arrow is pointing up, so that means it will have less length. So force normal will be only about this long. So notice I'm going to get this length, I'm taking it away from force gravity. So it is this length that now will be force normal. Force normal. So if you're pulling up, force normal is going to be less. If you're pushing down, force normal is going to increase quite a bit. Why is that important? If you look at the formula, force of kinetic friction, it is the constant for kinetic friction times force normal. So the higher force normal becomes, the more friction you're going to experience. So scenario A has a very large force normal, so therefore that's going to give you a lot of friction. And more friction means that it's going to be more difficult for you. In scenario B, force normal is much smaller, so therefore your friction is much smaller, so therefore less friction equals easier for you to push. Alright, so scenario B would be the ideal scenario. Alright, that goes ahead and takes us to the end of the lessons for this week, and thank you for watching.